In this video, we're going to look at the evaluation of one integral that has the square root of a squared in the denominator, and the other one has it in the numerator. Now, the first one can be done easily using a trig substitution. I've done that in other videos, and I've used this particular formula that I'm going to derive in other videos. Sometimes the instructor might not let you use it. He wants you or she'll want you to use the trig substitution. But let's see what we get for the first one, even though we've done it before. So here's the substitution we're going to use. X equal to a sine theta, which implies that sine theta is equal to x over a. Then dx, taking the derivative here, we get a cosine. Derivative sine is cosine, so we get a cosine d theta. We plug in the value of x into the radical here, and we get a sine theta squared. Factor out the a squared there, and we get 1 minus sine squared in the radicand times the a squared. But 1 minus sine squared theta is cosine squared. Take the square root, we get cosine. No absolute values, because we're assuming that the theta that we're going to use is acute, and everything, all the trig functions are positive for an acute angle. So we get this result. So let's convert the integral then. We had 1 dx, and dx is a cosine theta d theta. So it'll be a cosine theta d theta. And that's over this radical expression, which when we plug in the value of x, which is a sine theta, as we see here, you get a cosine theta. So the a cancels, the cosine and the cosine cancel. So we're left with 1 d theta. So we evaluate 1 with respect to theta. We get theta plus the constant of integration. We always go back to the original variable. So here I have sine theta is equal to x over a. The original variable is x. So taking the sine inverse on both sides here, on the left side we get theta, and on the right side we get sine inverse of x over a. Of course, we have the constant over here. So we just replace it then. The theta can be replaced by sine inverse of x over a. So if this is one of the formulas that your instructor allows you to use on a test or homework, then any time you have a problem like this, a constant here, because remember, you can have any constant here. This could be 10, and you can always bring it out. So any constant here, let's just call it k in this format. Then the answer, assuming you're allowed to use this formula, is just going to be sine inverse of x. Now this could be, maybe in some integrals you used a u substitution first, and maybe this is in terms of u, and then maybe u is 4x or x squared. Then you plug that into the final answer. And let's say this is a 9. 3 squared is 9, so the a would be 3. And you would just plug it into this formula. But for this one, this is the answer. The integral of the given integral, 1 over the square root of a squared minus x squared, is given by sine inverse, or arctangent, of x over a plus the constant. So now, from now on, assuming you're allowed to use this formula, you can just plug directly into this one. Now for this one over here, we're going to do the same sort of thing. We're going to find the value of this integral using the same substitution, because we have the same setup, except it's in the numerator. So this is going to equal to the integral of, same thing here, right? Plug the values in, you're still going to get, for the radical, you're going to get a cosine theta. And then for the dx, you're going to get a cosine theta, d theta. And then we continue here, multiply through, get a times a. That's a squared. I'll put it outside. Here the a is understood to be a constant. A is a constant, so I can take it outside the integral. A squared, and then I'll get a cosine squared theta, d theta. And this would have been easy if this was just cosine to the first, but we have a squared there, so we've got to reduce this, reduce that power, and that's using your trig identities here. So we got one identity that tells me that cosine squared theta is equal to 1 plus cosine of 2 theta. And this is over 2. So the identity tells me that cosine squared theta is equal to 1 plus cosine twice the angle theta over 2. Again, that's a constant, so I can put it out here. Now we're ready to integrate with respect to theta. So I'll leave the a squared over 2 out here. Integral of 1 with respect to theta. Theta, this plus. Integral of cosine is sine of the same angle, so in this case it's 2 theta. And then you got to use your chain rule in reverse. The derivative of 2 theta is 2, so got a 2 down here then. And we have the constant of integration. And then to simplify this, sine of 2 theta, again using another identity, that's equal to 2 sine theta cosine theta. And then this 2 right here will divide out, and this 2 right here will divide out. So let me continue up here now. I shall have the a squared over 2 out in front. And then I've got the theta here. And then it's plus sine theta, cosine theta, plus the constant of integration. Now, of course, we need to write the answer in terms of the original variable. We have it in theta. This is the answer in terms of theta, but we have to go back to the original variable x. So these are still a constant here, a squared over 2. And of course, theta, we do it the same way we did it in problem 1, in the first integral. Taking sine inverse of both sides gives me theta is equal to sine inverse of x over a. So for this one then, I get sine inverse of x over a. And now, sine theta, of course, we already did that right here. Sine theta is x over a. So this is plus x over a. And that's times cosine of theta. Now we can use some trig identity to get the cosine, but you can also get it by completing this triangle. We know sine theta, this is theta here, is equal to the opposite, which is x, over the hypotenuse. Let's say there. And then the adjacent side here is the square root of a squared minus x squared. So from the triangle, we want the cosine. We want everything in terms of the original variable x. So from the triangle, we know the cosine of the angle theta is the adjacent over the hypotenuse. So this will give us then the square root of a squared minus x squared over a. Then we have plus the constant of integration. Now let's just multiply through, distribute here, so a squared over 2 times the inverse there, so a squared over 2 times the sine inverse of x over a. And then it's plus. So this product down here is going to give me an a squared, but I'm going to distribute with the a squared over 2. So that's going to cancel the a squared and the a squared over here. So that's going to be with x over 2. So in front here, I get x over 2. That's going to be times square root of a squared minus x squared plus c. So again, a squared over 2 multiplies sine inverse of x over a plus x over 2 multiplies this radical expression over here, the square root of a squared minus x squared. Then it's plus the constant of integration. So now, again, once you have access to this formula, whenever you have a problem in this form, right here, has to be in that form. Now you can have a constant out here, that's okay. Or you can have a constant right here and then just factor it out. As long as you can get this look right here. Now, in some cases, this might be 3x squared. Constant 3, and then the x squared. So you could use a basic u substitution and get it in the form where you have it either, it could be a squared minus x squared, square root of a squared minus x squared, or it could look like a squared, square root of a squared minus u squared. And the u would be in terms of x. So this x here could be 3x over something. And notice this number here, square root of that, this is the same one. This a here, again, is this a over here. Just plug it into the formula. Thanks for watching. We'll see you next time.